Hello and welcome back to Unit 4. In this part, we are going to be looking at examples. In this unit, we've been developing Newton's laws, and in this last part, we're really going to be looking at how to apply them and use them to analyze what is going on with an object. I'd like to begin by giving you idea of how to approach these problems. So first, draw a picture. Again, pictures help organize what is going on in the problem, helps you see what is happening. Determine what the problem is asking for. This step might happen after the next step, depending on what's going on. The next step is to draw the free body diagrams. In your free body diagrams, include a coordinate system. What directions are positive? Label all your forces. Again, if you don't like my way of doing it with the subscripts and everything, come up with your own that works for you. Okay. Include the expected direction of the acceleration next to your free body diagram so that you have an idea of whether it should be positive or negative in your coordinate system. If you have forces that are not lying along one of the directions of your coordinate system, you have to resolve them into components. Then you have to do Newton's second law in both directions, the horizontal or the x direction and the vertical y direction. And often you have to solve the resulting equations simultaneously. Okay. Our first example is going to be revisiting projectile motion, though really I want to think about free fall. Okay. Let's start with where we were in the last unit, working without air resistance. If I don't have air resistance acting on my object, then the only force on it is the gravitational force. And here I'm using B for ball. It works for me. Okay. If I now think about Newton's second law, F net equals ma. I'm going to rewrite the forces in terms of the forces on my object. Well, I only have one, and that's the gravitational force. The acceleration of this ball will be downward. We can plug in that the gravitational force is the object's mass multiplied by the acceleration due to gravity. And not a huge surprise, we get the acceleration is equal to the gravitational acceleration in this case. Okay. If we now think about what happens with air resistance, so we're going to be moving upward, velocity upward. Okay. We also know that as things move up, typically, if they're just in projectile motion, they slow down, which means the acceleration again has to point downward. Okay. In this case, we have two forces. We have a gravitational force, and we also have a frictional force due to the air resistance. Okay. Because the velocity is upward, air resistance will point downward because it always points opposite the direction of the velocity, just as every type of friction does. We can now again do F net equals ma. In this case, I'm going to take and add my two forces together because they're in the same direction. Set that equal to the mass multiplied by the acceleration. Everything is downward, so it makes sense in this coordinate system to let down be positive. And now I can write that the acceleration will equal the acceleration due to gravity plus the force of friction divided by mass. And you can see in this case, the acceleration has to be greater than the acceleration due to gravity. On the other hand, if we are moving down and we have air resistance, the frictional force will now be up. Gravitational force will be down. Let's again let positive be downward, and if anything, the acceleration will be downward again. As objects fall, they gain velocity. So again, applying Newton's second law. In this case, my forces are in opposite directions. So I'm going to take everything in my positive direction, subtract off everything in the opposite direction. Okay. One thing to notice here is it's possible for the acceleration to equal 0. Okay? The acceleration will equal 0 when the gravitational force equals the force due to air resistance. So A equals 0, then WEB equals the air resistance. And the velocity is constant. Okay. This constant velocity has a special name. This is the terminal velocity. Okay. But let's assume we're not in that situation and we are still accelerating downward. Okay. In this case, we can write that the acceleration will be the acceleration due to gravity minus the frictional force divided by the mass. So we can see the acceleration will be less than the acceleration due to gravity. Okay. When we put air resistance in, the symmetry of projectile motion is broken because our acceleration as the object moves up no longer equals the acceleration as the object moves down. Symmetry is broken. Not only that, typical models of air resistance have the force due to the air resistance dependent upon the velocity. So the faster you are moving, the bigger the air resistance will be, and therefore we are no longer even in a constant acceleration situation. At the top of the motion, for that instant when the ball stops moving, the acceleration again equals g. It has to go from being greater than the acceleration due to gravity to less than the acceleration due to gravity, which means it has to pass through the acceleration due to gravity. That happens at the very top. Next is an elevator problem. I've mentioned it. I do like elevator problems. Okay, so here we have a 60-kilogram person standing on a scale in an elevator, because that's what everybody does, right? Oh, it's got a typo. It used to be a book. Now it's a person. Okay, fixed. Okay, we want to know what is the normal force holding this person up given the elevator accelerating upward, moving at a constant velocity, or accelerating downward. Okay. So first, a couple of numbers that we will be using repeatedly throughout this problem is the elevator's weight, which will be the mass due to the acceleration due to gravity. We're told, or not the elevator's weight, the person's weight. And that should be a P, not a B. I'm having issues. Okay, here we go. P. 60-kilogram person times 9.8 meters per second squared, and that equals 588 newtons. We're also going to need mass times acceleration. In both cases, our acceleration is 2 meters per second squared. Direction changes, but we can put in a direction later. So this is going to be 60 kilograms times 2 meters per second squared, which is 120 newtons. We can draw one free body diagram for all three cases. So if we look at the free body diagram of the person, we have the normal from the scale on the person. and the person's weight. And remember, this is the value that the scale reads. We discussed this a couple of parts ago when we looked at the free body diagram for the scale in the elevator. For all parts, I'm going to let up be positive. So now when I do F net equals MA, I take my normal force in the positive direction, subtract off the weight, and that equals MA. And I'm going to leave the vector sign over the acceleration because it might be upward, it might be downward. I'm going to need to adjust the sign of that term. I don't know it yet. Okay. But I can solve for the normal force equal to MA plus the weight. Okay. Now notice the directionality of the weight has been taken into consideration. It's that minus sign right there. So this number will always be a positive 588 newtons. I've already taken the directionality into consideration. Now let's break into the three parts of this problem. Okay. For part one, my acceleration was upward, which is my positive direction. So I'm going to put in a positive 120 newtons plus 588 newtons, and that will give me 708 newtons. For part two, the acceleration was 0. So I'm going to have 0 newtons plus 588 newtons, which equals 588 newtons. And for part 3, the acceleration was downward. So I need to put in the negative sign on that one to indicate downward. Remember that negative sign is downward. Okay, so what we see is that when the elevator is moving or accelerating upward, the scale is going to read greater than the person's weight. When it's moving at a constant velocity or stopped, it will read the person's weight. And when it's accelerating downward, it will read less than the person's weight. Okay. We can think about when each of these motions or when each of these readings will happen. So if I have a building, say Byrd Science Center, with 3 floors, 1, 2 is probably a little bit high, but that's okay, 1, 2, and 3. Okay. If I get into the elevator on the first floor, press the buttons, it's going to start moving upward because that's the only upward direction. So in that case, I'm going to have velocity and acceleration upward, and my scale is going to read, using those numbers, 708 newtons, but I'm just going to do greater than my weight. Okay. As I pass the second floor, my velocity is constant, so I will get a scale reading equal to my weight. And as I approach the third floor, my velocity will still be upward, but my acceleration has to be downward in order to slow the elevator down so it can stop, in which case it will read less than my weight. Okay. I can then imagine getting back in on the third floor and heading back down. Well, the first thing that happens is the velocity and acceleration are in the same direction, causing it to move downward. So the scale will again read less than my weight. As I pass the second floor, still going to have a constant velocity. And as I arrive at the first floor, my velocity will be downward, my acceleration will be upward again, and my scale will again read greater than my weight. Okay. Now your question might be, does this actually happen? So I have a YouTube video. Now ordinarily I would play this YouTube video for you, but I'm not sure if it will let me get away with that. Even though it's my video, it's me getting on the elevator on a scale in Bird Science Center. You can go and watch the readings and how they change. Okay? So I encourage you to watch this video. Given all of this, does a normal force on an object always equal its weight? And the answer here is a big resounding no. We just saw how on an elevator it fluctuates depending on whether or not it's accelerating. Okay. It's also going to depend on what other forces are acting on the object. Is there another object sitting on top of it? Is there a rope or something pulling on it? What else is going on? So the answer here is a resounding no. Okay. Our next question involves curling. Curling is a sport. You can see it in the Winter Olympics, where they take large stones and push them down sheets of ice, trying to get as close to a particular mark on the ice as possible compared to the other team. Okay. Curling stone has a mass of about 18 kilograms. The sheet of ice is about 40-meter long. It does take about 8 seconds. And we want to know what is the force of friction between the ice and the stone. Okay. This is where a picture comes in very, very handy. So let's draw a picture. Here is my curling stone. They usually have a little handle like that. I'm going to call this a position of 0. And somewhere down here is 40 meters. Okay. It is given some initial velocity, causing it to move down the curling, I think it's called a pitch, curling pitch. And as it goes, it's going to slow down. So the acceleration will be in the opposite direction, such that when it hits the 40-meter mark, it is stopped. Okay. We also know that at the 40-meter mark, it is 8 seconds after where it started. Okay. We can also look at the free body diagram for the curling stone. We have a normal from the sheet of ice. Oh, let's not do S for that. Let's do I for ice, so we can use S for stone. We have the stone's weight, and then we have friction in the direction of the acceleration, causing this stone to slow down. Really quick, as an aside, something I should have said. If you've watched curling, you know that the teams are on the ice with the little brooms, sweeping happily away, trying to make it do what they want it to do. We're going to ignore all those effects. They're not sweeping in this case. Okay. I want to know how big the force of friction is. So, well, the force of friction will be, in this case, equal to the mass of the stone multiplied by the acceleration. And it will be in the same direction, so I've got that down. In order to solve this, I need to know the acceleration of the curling stone. And if you look at our drawing that we have, it's a whole lot of what we did last unit with projectile motion and constant acceleration. It even tells you to assume a constant acceleration. So we need to go use our constant acceleration equations. Okay. I let positive be to the right. With that assumption, I can now, okay, I can now write my grocery list. Okay, what do I know? I know that my final position is 40 meters. My initial position I defined as 0. My final velocity is 0, but I don't know the initial. The acceleration is what I want to know, and I know the time of motion was 8 seconds. I know lots of information about positions, but I can't use the x equals x naught equation right yet because I don't know v naught. I also can't use the v equals or v squared equals v naught squared equation right off because I don't know v naught and I don't know a. So the first thing I need to do is combine my equations to remove v naught and put in v. The easiest way to do that is to start with this equation. So v equals v naught plus at, and solve that for v naught. And that equals v minus at. I can then go to my x equals x naught equation and plug in what I just had above for v naught. Getting rid of the parentheses. Now I can combine like terms. So now I have an equation that only involves things that I know with the exception of the one thing I want to know, allowing me to plug in. So 40 meters equals 0 meters plus 0 meters per second times time minus 1/2 times the unknown acceleration times the time, which is 8 seconds squared. I could have plugged it in over here on the second term as well, but it's multiplied by 0, so it doesn't matter. This allows me to solve for the acceleration equal to negative 1.25 meters per second squared. And if I go back, I realize I defined to the right as positive, so I should have accepted or expected my acceleration to be negative. Okay. So my acceleration is to the left and has a value of 1.25 meters per second squared. And I've gotten rid of that negative sign because the arrow gives the direction in this case. I can now come over to my formula for the frictional force and plug in 18 kilograms times 1.25 meters per second squared. And that works out to be 22.5 newtons. Okay. And in this case, given the drawing we've done, we can put in a little note here that this is to the left based on our drawing. Okay. One last example for pulling a block. We have a 60 kilogram person pulling a 30 kilogram block across the ground with a rope and an acceleration of 0.5 meters per second squared. We're going to assume that the rope is pulling horizontally and that the friction between the block and the ground is 10 newtons. And we want to know what is the tension in the rope and what is the force the person is putting on the ground. So this looks like this. We have our block, we have a rope, we have a person pulling on the rope. We know the acceleration is this way with a value of 0.5 meters per second squared. And we know we have friction between the ground and our block of 10 newtons. Okay. If I look or consider this, I want to know the tension in the rope. In order to find the tension in the rope, I need to consider the two objects, the block and the person, separately. So I'm going to draw two free body diagrams. Beginning with the block, I have the normal force from the ground on the block. I have that frictional force between the ground and the block's weight, and I have the tension in the rope on the block. This force I know is 10 newtons. It's given in the problem. I'm also going to put next to here that my acceleration is this way, and I'm going to let the positive direction, my coordinate system, have positive to the right. Now if I look at the person, I have a very similar free body diagram. I have a normal from the ground on the person's weight, a force between the ground and the person. This is the other force that is being asked for in the problem. And again, a tension in the rope on the person. We are going to make an assumption in this problem. And that assumption is that the rope tension is the same everywhere, which allows us to say that the tension in the rope is the tension in the rope. Under what circumstances would that assumption not hold? If the mass of the rope was comparable to the block or the person, or if the rope was able to stretch, all bets would be off. But let's work in the assumption that our two tensions are equal, and in fact, let's just let them equal T to make life easier. And that's the wrong one. Let's set the tension equal to T, shall we? It's this one. Okay. If I look at the person's free body diagram, it involves both forces that I don't know. So this is not a good place to start. Therefore, I'm going to start by looking at the forces on the block. And if I think about the forces on the block, the only two that can contribute to the acceleration are the tension and the frictional force, because the normal force and the weight act perpendicular to the acceleration. So I'm only going to look horizontally. F net is going to equal the mass of the block times the acceleration. I'm going to take every force in the direction I've determined to be positive, that's the tension, subtract off the force in the opposite direction. Again, mass of the block times A. This allows me to solve for the tension. It will equal the mass of the block, which is 30 kilograms, times 0.5 meters per second squared, minus the frictional force, which was given in the problem as 10 newtons, and that works out to be 25 newtons. Now that I know the tension force, I can use the person to find the force between the ground and the person. So I have the force from the ground on the person minus tension equals the mass of the person times acceleration. Therefore, the force from the ground on the person will equal 25 newtons, the tension, plus the person's mass times the 0.5 meters per second squared acceleration. And that works out to be, almost out of room, but I'm going to squeeze it in at the bottom, 55 newtons. This concludes this part of this unit, and this unit for that matter.